So we are very glad that we have together with us Dr. Konidakis. He has a PhD from University of Glasgow. He's a very experienced postdoc. He works in the Institute of Electronic Instructions and Lasers, and he will present us one of his activities that relates with the time-resolved transient absorption spectroscopy measurements, particularly applied for perovskite solar cells. So, Ioannis, the floor is yours for the next 45 minutes. Okay. 10 minutes before I will notify you.
Okay, perfect, Kostas.
Thank you very much, Kostas. Good morning, buongiorno. My name is Ioannis Konidakis. I am a postdoctoral researcher at the Institute of Electronic Structure and Laser at the Foundation for Research and Technology, which is located in Heraklion, Crete. And today I will speak a little bit about how we employ time-resolved transient absorption spectroscopy in order to study perovskite solar cells and perovskite components for solar cells. Before I start, let me thank the organizers for organizing this meeting, and of course for inviting me and giving me the opportunity to speak here today. And our lab is the ultra-fast laser, micro and nano processing laboratory, which runs under the supervision of the research director, Dr. Emmanuel Stratakis. Emmanuel gave us a lecture on the opening day of this intensive course, so most probably you will have a glance of our research activities already. So we specialize a lot on the ultra-fast laser processing and theoretical modeling of materials. We do a lot of ultra-fast spectroscopy in optoelectronic devices, and that includes photovoltaics. We do laser engineering of spectroscopy on graphene and related 2D materials. We do a lot of synthesis by means of using laser beams for nanomaterials, and that includes perovskites. We use lasers to fabricate biomimetic surfaces and scaffolds. And lately, we also have a great activity that we develop a nonlinear imaging microscopy for optical diagnostic tool. So today, the outline of this talk will be, I will start with some brief introduction to perovskite solar cells. That includes the device configuration, the operation principles, what we have achieved so far, and what are the challenges. And then I will speak a little bit about how TAS comes into play and why it's important to probe charge carrier. Sorry. Okay. Thank you. Okay, more worries. Then I will, as I said, I will talk about how TAS is important for studying perovskite solar cells and perovskite and components for perovskite solar cells. And I will present 3 different examples. The first will be in perovskite solar cell devices that we employ different whole transport layer polymers. And I hope I will be able to demonstrate to you how we correlate the electrical performance with the perovskite morphology and the charge extraction dynamics. Then I will speak a little bit about a method to develop perovskite films that is without doing thermal annealing, which is a typical method for making the films. And it is by means of laser-assisted crystallization. And we believe that this is a method for improving charge extraction processes. And then I will, at the final part of the talk, I will talk about a little bit how we perform in situ monitoring of the charge carrier dynamics of perovskites while doing transient absorption spectroscopy during the perovskite crystallization. And then I will summarize up with the conclusions. So I'm sure everybody in this room, you have heard the word perovskite, no matter what your scientific background is. These materials are very famous nowadays. And we can have organic and inorganic perovskites that attract significant attention, scientific attention, due to their potential for being components of next generation photonic applications with advanced properties. And that includes also photovoltaics. We can meet these guys in LEDs and in solid state lasers. So this is the basic structure. So you know of, it's ABX3. where you have a large organic cation sitting in the middle of 4 octahedra, which each octahedra has one metal cation in the middle, and on the edges you can find the anions. Now, in brief, if someone wants to summarize with a few words why these materials are so important, it is because they have a medium optical band gap, they have a strong absorption coefficient, and long carrier diffusion length, low recombination losses, and more importantly, we can tune the band gap by altering their structures. So these are generally advantages in terms of implementing these materials in photonic applications. And when it comes to solar cells, the question is why to choose perovskite light absorption components for photovoltaics. And the answer lies within this chart. You can see that the perovskites within the last decade or so, there is a big improvement in the power conversion efficiency from 4 to 22, even I think a little bit more nowadays. And on the other hand, for the other types of photovoltaics like the organic or silicon, etc., it took several decades to reach this point. So people believe that this is going to be the component of next generation photovoltaic devices. So efficiency is one thing. They also can be done in flexible structures and in large scales, and with generally low-cost processes. So they have a lot of advantages, but of course, the ongoing scientific challenge remains to maximize the efficiency while at the same time improving the device stability. But before I talk about what are the ways to tackle these problems, let us have a look on typical components of a perovskite solar cell device. This is a demonstration of the planar inverted configuration when you have the glass substrate at the end, then you have an indium tin oxide electrode, cathode electrode, and on top of that, you need a polymer material which acts as a Hall transport layer. And of course, you have the main component, the head of the perovskite solar cell, which is the perovskite film. And on top of that, you have the electron transport layer electrode, and then you attach the metal electrodes at the top. Now, as I said, the ongoing scientific challenge remains to maximize the efficiency and keep these devices stable. And in order to do this optimization, several approaches have been adopted over the years. So the first one is to vary the perovskite composition itself. The second is to explore different crystallization and deposition protocols. And of course, the other one is to select different types of polymers for Hall transport layer or electron transport layer materials. And the two crucial parameters that people acknowledge is the crystalline quality itself. So you really need to have a very good perovskite crystal, and of course the interactions of this crystalline layer with the HTL and the ETL interfaces. So in a typical photovoltaic process, you have 4 basic steps for energy conversion. First, you will have the light absorption and exton creation. Then you have the diffusion of extons, and then the exton disruptions and free charges. And then you have the charge transport of the free carriers and to the electrodes. And that is the process of the energy conversion in a typical photovoltaic case. Now, how fast we can extract the free charge carriers from the perovskite materials is it will be a direct fingerprint of the device performance, and that's where TAS, time result transient absorption spectroscopy, comes into play and can offer some information, because it provides significant insights on how the charge carrier extraction dynamics and recombination processes occur within these perovskite components. And by knowing this and having knowledge of this process, we can then design and develop advanced perovskite solar cells while we correlate the charge extraction dynamics with the morphological characteristics of the films. So that's why transient ozone spectroscopy is so popular when it comes to photovoltaics, and several groups have used this technique in order to study the dynamics. And of course, the very famous labs here. So let me show you the first of all, the schematic representation of our experimental setup. We actually employ a Newport TAS1 spectrometer, which is presented here. And as a fundamental beam, laser beam, we use the primary laser of our lab, which emits at 1026 nanometer with a pulse of 170 femtosecond and a kilohertz rate. So we take the fundamental beam, we use a beam splitter to split the beam. As Professor Lazzani gave us a very nice introduction in the fundamentals of TAS, the first thing you need in a pump probe experiment, you need a pump beam and a probe beam. So the first thing to do is to split the beam, and you have most of it, 90%, acting as a pump, which is directed with mirrors through a neutral density filter and then through a chopper in order to have this on-off situation that we need, and it ends up in the perovskite sample. And then, of course, it is blocked. On the other hand, the other 10% of the fundamental beam acts as the probe, which is directed through mirrors to a delay stage, and then is directed to a crystal in order to generate white light generation. And you can have then a spectral range of 500 to 1,000 nanometers of recording. And this instrument can operate to a time window up to 1,000 picosecond with a resolution of 2 nanometers in the wavelength range. Now, the one thing that I would like to emphasize here is that when it comes to perovskite materials, up to now I mentioned only the good things about perovskite. I forgot to mention that they have a tendency to degrade when they are exposed to humid air and moisture. So, and that's why people try to identify ways in order to stabilize these materials. So it is very important, we found out that it is very important to exhibit all the transient absorption spectroscopy measurements and in general all the characterization procedures while the sample remains under inet conditions. So we place this specially designed holder within the glove box where the perovskite synthesis is done. And here we perform TAS analysis while the perovskite remains under nitrogen in order to avoid degradation effects. Because a perovskite film normally will degrade within a day. So if you measure the spectra in the morning, it will be quite different with the one that you measure in the afternoon. So remember that this perovskite material have to be studied. It's important to study them under inet atmosphere conditions. So here is a typical spectra of a methylammonium lead iodide perovskite, where you can see it's actually a 2D contour graph, but you can see time, how the time and wavelength here, and of course you can see how the difference in the optical density absorption changes both in time and with wavelength. Sorry. So basically here, the difference of absorption is the logarithm when the beam is blocked over when the beam is unblocked. And if we do that, it ends up with the optical density of the probe without only the optical density of the probe minus the optical density of the pump plus the probe. So in this configuration, the photo-induced bleaching will be as negative due to the excitation of the valence bands electrons to the conduction bands, which means that we'll have fewer photoreceptors in the ground state in order to absorb the probe light, whereas in case that you have positive photo-induced absorption with delta OD positive, we'll have less light detected when the sample is excited. Now, let us move on to the first set of results. So it will be TAS in perovskite solar cell devices. Then we will talk about how we implement TAS in laser-assisted crystallization, and then we'll see TAS during the crystallization itself. So the architecture of the fabricated devices, of course, for this we collaborate with a great team of Professor Kimakis. It used to call Technological and Educational Institute of Crete. Now Kolsas needs to correct me. This is the Mediterranean University, okay? So apologies for this, but we thank the guys a lot for providing us the samples. So as I said, they make nice samples of these planar inverted configurations. And the thing I would like you to notice here is that we make two sets of samples. One, we employ PEDOT-PSS as a whole transport layer, and in the other sets, we employ PTAA, which is more hydrophobic, as you can see from the, with respect to PEDOT. And the thing that we want to explore is what will be the difference in the morphology of the perovskite and in the photovoltaic properties of these devices by simply employing different whole transport layers. And let me show you first how we make these devices. So the typical thermal annealing crystallization is shown here. And keep an eye on this, please, because then I will explain some difference when it comes to the laser-assisted crystallization. So in a typical thermal annealing crystallization, you first spin coat on top of the HCl polymer, the lead iodide solution. Then you heat it up at 100 degrees for 10 minutes. So, and then you add the methylammonium iodide solution and you heat it up for another 30 minutes at 100 degrees. So you will need around, let's say, 40 minutes of annealing, of thermal annealing, to make these devices. Now, as I said, we would like to see what will be the difference in the perovskite morphology when you grow the perovskite on top of a different HCl material. And the first evidence come from the scanning electron microscopy analysis. And you can see here on the right that the perovskite, the lead iodide perovskite, which is on top of the more hydrophobic PTAA polymer, exhibits considerably larger grains than the one when compared to the one which is grown on the PEDOT-PSS surface. And usually larger perovskite grains means that they will be of better quality and they will perform better when it comes to power conversion energy of the photovoltaic device. And the first evidence for this, we measure also the photoluminescent intensity of these two films, and by applying micro-PL technique, and we can see that the film on the PTAA surface has a 20% better quenching than the one in the PEDOT surface. So this is the first indication that we will have faster charge extraction transport dynamics at the PTAA methylammonium lead iodide configuration. And of course, when our colleagues there did these photovoltaic measurements, they confirmed this. So this table shows the average parameters extracted from 24 cells. And you can see the current and voltage curves here. And it becomes immediately obvious that, and remember this is the average, not the champion devices only, that by simply introducing the PTAA polymer as a whole transport layer, you raise the power conversion efficiency from 20.6 to almost 15.6, which is an enhancement of 24%. And this is mostly attributed to the increase in the VOC, in the open circuit voltage. So, okay, we see that on top of the PTAA polymer we have better perovskite grains. We see that this resulted to better photovoltaic performance. And now, in order to understand the origins of why this is happening, we apply transient absorption spectroscopy. And here is a typical spectra of the PEDOT-PSS methylammonium lead iodide structure. So you have the HCl and the perovskite configuration. And you can see this photo-induced bleaching, which is the characteristic of methylammonium lead iodide perovskite at 750 nanometers. And of course, we can see some photo-induced absorption in lower wavelengths. Now, as you can see from this plot, the black line represents the photo-induced bleaching with no delay at 0 picoseconds, where as time progresses, the photo-induced bleaching diminishes. And the real information about the charge extraction dynamics comes when we want to study the kinetics of the relaxation dynamics of these decay processes. So here there are plots of the delta OD photo bleaching and how it decays with time. And the symbols are the actual data, while the solid lines are fittings that I will explain in a minute how provide us the charge carrier dynamics that we are interested at. So the first fitting model that is available in the literature and we try to follow is based on a 3 exponential fitting model when it provides us 3 different time components. The first time component T1 represents the charge carrier trapping at the perovskite grain boundaries. The T2 component represents how fast the electron hole transfer process occurs from the actual perovskite layer to the HCl polymer. And of course, you have a larger T3 time component, which provides evidence about the electron hole recombination times. And it is generally acknowledged when you follow this model that the critical component is the T2 when if you have faster and more efficient charge extraction from the perovskite layer to the electrodes, you will end up with an enhanced photovoltaic performance. And so if we apply this model in our cases, we can immediately see that this T2 time component for the case of PTAA polymers is significantly faster, which means that we have better extraction of the free charge carriers from the perovskite film to the whole transport layer material, which is PTAA in this case. So we also have some quicker trap fillings and faster hole extraction. So this is why the physical origin of the better power conversion efficiency. But there is another model which is more widely accepted, I would say, that it is the polynomial fitting model. And instead of having the time components, we here talk about kinetic rates, how fast this process occur. And we do the fitting by employing this polynomial equation, where N is the photo-induced charge carrier density, K1 represents the trap-assisted recombination rate, K2 represents the bimolecular recombination rate, whereas K3 represents the ozone recombination rate. So again, it's the same set of data, but with a second fitting approach. And we can see that the K2 parameters for the PTAA polymers are lower, and this is indicative of longer charge carrier diffusion lengths. So in the PTAA polymer, let's say, not only it uses better charge extractions, but the free charge carriers can diffuse better and longer penetration lengths within the actual perovskite film. Now, let us move in another set of results. Here, as I said, we tried to fabricate perovskite materials by means of laser-assisted crystallization. And of course, the first question that we have to answer is why you need to do this. And remember when I show you the typical procedure of preparing perovskite solar cells by means of thermal annealing, you will require like an hour to do so and heating of the sample. And when it comes to fabricating perovskite solar cells in large scale and industrial scale, this will be costly. So people look for alternative ways to crystallize perovskites. And we are from a laser lab, so we try to do this with the laser. And The main advantage of this is that you can do it very rapidly. You can do it, let's say, in a few seconds. And not only you can do it very rapidly, but the first reports show that you can have perovskite crystals of better quality, more dense, and with larger grain sizes. And the second important advantage is that when you have the precursors and you heat them, you create the perovskite film in all area. Whereas when you use a laser beam which is focused, you can have the controlled growth of perovskite structures, and you can create microchannels, let's say, or whatever structure you like. So the first advantage is that you can do it very fast, and you can end up with better quality of crystals. Whereas the second advantage is that you can do it and you can control the shape and the size of the grown patterns. So we try to do it in our lab, and in order to do so, we still have the precursors of the perovskite, the deposition of the whole transport layer materials, which again will be PEDOT or PTAA, is exactly the same, up to the point where you have the precursors. But then, instead of using the heating procedure of typical thermal annealing, we employ a laser, a CW green laser at 532 nanometers. We use some main optical components to have a homogeneous laser beam on the surface of the precursors, and we can immediately find out that we can crystallize the perovskite by simply using, let's say, small radiation doses, and most importantly, within a few seconds. So all these scanning electron images are after 20 seconds of laser radiation. And of course, the one thing that it became clear from the very beginning is that the employed laser fluence significantly affected the grain size of the perovskite itself. And remember from the first case study that I'll show you today, that the grain size are important when it comes to the quality of the perovskite crystals. So this is the dotted line here shows the best, let's say the biggest grain that it was achieved with thermal annealing, whereas with the laser-assisted crystallization, we were able to grow perovskite grains considerably larger and, as I said, a lot faster. And of course, here you need to be a little bit careful, because in the lower laser fluencies, you don't achieve so good grains. When you reach a point where you have the optimum grain size formation, but then if you keep on irradiating the sample, you start ablating it, and then the grain size drops again. So, but this is let's say the best parameters to do so. So immediately we would like to check how the introduction of this new protocol affects the charge carrier dynamics and the recombination rates within this set of films. So this is a busy slide, but then again we perform task analysis of all the laser-assisted samples that we made in different fluencies, and we compare that with a reference sample which is created by thermal annealing. And it becomes apparent that all laser samples exhibit faster T1 and T2 components, which means that they have faster trap fillings and faster charge extraction dynamics. Whereas the optimum among the lasers, among the ones that they were created by laser-assisted crystallization, the one that had the largest grain size exhibits also the faster charge carrier extraction dynamics. So for the laser-assisted films, we have quicker trap fillings, faster hole injection, and slower recombination rates. We also have lower K2 rates that are indicative of better diffusion lengths within the perovskite of the material. So this study shows a direct correlation between the extraction dynamics and the morphology of the perovskite films. Now, remember when we were talking about the devices, we said that the PTAA polymer was more efficient, and we decide to try the laser-assisted crystallization on the more hydrophobic PTAA film. But unfortunately, that was not so successful. Here is a scanning electron image of perovskite film from the typical thermal annealing. Here is the best perovskite film that we could obtain upon adopting the laser-assisted crystallization protocol, and we see that the latter protocol doesn't seem so advanceful in terms of creating perovskite grains. And we also, from the corresponding XRD files, spectra, we see that we ended up with a lot of lead iodide excess. And we have an explanation for this that I would briefly like to mention, is that here you have, it's more hydrophobic, and you really need to do it slow in order to have a homogeneous deposition of the precursors onto the film. When you try to accelerate the process, we believe that the methylammonium lead iodide solution evaporates, and it leaves behind massive excess of lead iodide film, and of course smaller or not larger grains when compared to the thermal annealing, the samples from thermal annealing. Now, let me move to the final set of results that I will show today, which is a demonstration of performing transient absorption spectroscopy in situ while the perovskite crystals are formed. So we do in situ monitoring of perovskite charge carrier dynamics. And we would like to do this because we believe that this will be an important diagnostic tool in order to diagnose how the perovskite film will be during the fabrication process. Because up to now, in order to reveal optimum annealing periods for the HCl perovskite configurations, we have to rely, and people rely on post-fabrication characterization, which means that you make the device first, and then you go on and measure the power conversion efficiency. And if you ask Costa students, they will really appreciate, they would really appreciate, or Kimakis students, yes, Professor Kimakis students, they will really appreciate if they have, let's say, a way to find out whether a parameter will work better before they need to make all the stages for the final fabrication of the device. So we believe that we can assist the design and fabrication of better perovskite solar cells. And this is a work mainly done by one of the PhD students of our lab, Efthimi Serpetzoglou. And in brief, what we see is that we place in TAS, as I will show in a minute, the perovskite components without the crystallization being formed, and then we monitor how the charge extraction dynamics and recombination rates progress with time. And we will see that we'll find a time where you have the optimum annealing time, let's say, and if you continue heating and annealing the sample further, you start to have problems with the charge extraction and recombination processes. So how this is done, basically we use exactly the same test setup, but instead of having the sample holder cell, now we use a heating element within the sample holder cell. So the deposition of the precursors is exactly the same. You first deposit the lead iodide, you heat it up for 10 minutes at 100 degrees, then you spin coat the methylammonium isopropanol solution, and instead of heating it for the whole period, we heat it up while we perform TAS analysis. And we do that in 3 different temperatures, at 90 degrees, 100 degrees, and 110 degrees. And just to briefly show you that here is the delta OD plot of at the time when the time duration where the optimum annealing charge extraction dynamics were revealed. And you can immediately see that in the lower annealing temperature, this occurs at the same time for both PEDOT and PTAA, whereas when we go at the 100 degrees, the optimum annealing period is faster for the PEDOT PSS polymers, 55 minutes here instead of 75 minutes here. And you can see this also from the relaxation dynamics that are described here. So the conclusion for this is that the more hydrophobic PTA polymer requires longer annealing periods in order to achieve optimum charge extraction. And just to show you that, of course, keep in mind that transient absorption spectroscopy studies cannot be, it's also employed in different photovoltaics, like inorganic photovoltaics, that we can then again extract information about this relaxation phenomena. And it can also be done in glasses when we examine a little bit how the silver plasmon, the plasmonic features within the glasses that we make and we treat evolve with time. So we believe that TAS is also a good diagnostic tool in other type of applications. And with this, I would like to conclude my talk. So for the Perovskite solar cell devices, I hope that I demonstrate to you that by simply introducing the more hydrophobic polymer PTAA, we have better power conversion efficiency, and this was attributed to Perovskite configurations with quicker charge extraction dynamics of the PTAA polymer. When it comes to laser-assisted crystallization, laser-assisted crystallization results to the fabrication of methylammonium lead iodide films with larger grains and improved charge carrier dynamics. And we believe that this is the first step of introducing the laser-assisted protocol as a synthetic procedure for fabricating perovskite for photonic applications. And I also show you some of the advantages of performing in situ tasks during perovskite crystallization that allows the under-fabrication monitoring of charge extraction properties instead of doing the typical post-fabrication procedure. So I believe that these are three nice examples why transient absorption spectroscopy is a figure of merit diagnostic tool for optimizing photovoltaic performance and, of course, stability. And you could also find a video. I don't know if it is uploaded, but it is one of the courses of IPEN project. So please see this video as well if you like to see how the laser-assisted crystallization of perovskite films is done in our lab. And there are also 3 other videos. And with this, I would like to acknowledge my colleagues in Institute of Electron Extraction and Laser, and of course, our colleagues in the Technological and Educational Institute of Crete, Professor Kimakis, Mediterranean University, sorry, apologies for this. And of course, the funding that all this research activity is co-funded from several projects. And of course, you for your kind attention. Thank you very much.
Any questions? Questions? Yes.
You showed 2 models for the interpretation
Yep.
of the decay curves, and
Yep.
when you presented your results, you showed the 3 exponential. This is always a question which model to use and how to interpret the components. Would it be appropriate to show an average decay time in this case, or what's your?
People don't like this. I don't know. That's why when we analyze the data, we would like to use both models. This is the big debate, if you want to use the exponential one or the polynomial one. And if you decide to use the exponential one, I think the 3-time component is let's say, the most, I believe, the more accepted in terms of how people acknowledge it. But you mean in excluding an average time for the whole 3 processes?
No, I mean, the interpretation of the components is always a little bit tricky.
Yeah. That's why I said that this is, we just follow the literature, you know. We can...
I saw some data there, but goes up to 1,000 picosecond, I think.
Yes.
But then in the exponential time, you show 10 to 6.
Yes, this is the weakness of this. We know people that do it, they do like an extrapolation, and they believe that they have enough to see how this will extrapolate with time. I totally agree with you, but we were forced by a reviewer to do it.
Looking at the data with my eye, it seems to be 1 exponential decay. Depending on alpha n, alpha d, and alpha.
Yes, but I can explain later. It also depends on the fluence. If you as we increase the pump fluence, you'll have the second one coming in as well. So then it wouldn't be safe to use just one for the whole pump fluence that we use. But, we have tried all this. Yeah.
Any other question? I have a question. So I have one question. I have one comment and one question. I will start with the question. And the question has to do that you presented a very fast laser processing technique for crystallization.
Yep.
And then you compare with the classical way that we are doing in the laboratory.
Yeah.
But in the laboratory, we're building devices. From your measurements, I have not seen a device.
Yeah.
So how can you compare that this is better?
It's a little bit, I'll tell you, yeah. The idea is to make the device as well. We haven't done yet. Yes, there are some difficulties that we need to overcome, because what happens there is you really need to ensure that you can have a homogeneous area of the film in the whole perovskite cell area. These are perovskite, let's say, spot sizes, you know, and there is there is a little bit tricky, because what happens, you can do it, it's done, but then you kill a little bit the power conversion efficiency, because you form grain boundaries. When the laser scans the area, you have some overlap when the perovskite is crystallized and where you have precursors. And on the overlaps, you create a little bit of boundary situation that they create defects. You create defects, and we work on it. That's the plan, actually. It was a very good point. Of course, the plan is to make a device out of it, but it's not out yet. But I wanted to show the process.
Okay. And the comment has to do with the field quenching. The field quenching does not show faster extraction, shows more intense extraction.
Okay. Yes. That's okay. Good.
Any other question? So let's examine. Okay. The last moment.
One is does the perovskite solar cells are the same as the thin film photovoltaic?
Perovskite it's a film. It's like you mean like a thickness of 300 nanometers to 400 nanometers. It's a film. If you go back to the perovskite components, you see the red. It's a perovskite film, actually.
Okay, and
it's way back. Okay.
We have to the development of the transparent photovoltaics, which let most of the visual most of the visual wavelengths can go through.
Yeah.
And you can place the conventional parts in buildings like windows and stuff like that. How do you see this technology take part?
No. But you know, the perovskite, they absorb all the light.
They absorb, yes. They are very good light absorbers. So, or maybe if they are very, very thin. But okay.
But they absorb.
They absorb, yes.
The strong thing about the perovskite, the inorganic perovskite is the hybrid thing. No, they absorb the light.
So if you have a perovskite window, it will be almost like a shade, you know, like a curtain.
So how they come, what, do they bring something new to the industry instead of just building
No, the power conversion efficiency. People believe that if in a few years, this device will be like chumps. It will be very much more efficient than the ordinary photovoltaics, I would say.
The problem with the perovskite, as Yannis has mentioned in his talk, now this kind of efficiencies that they are reported are for small cells, like 0.5 millimeters, 0.5 millimeters. We move to the modules, then the technology changes a lot. So the efficiencies are dropped less than 10%. So now they are trying to combine now the silicon with the perovskite in order to keep, in the modules to keep, the efficiency, the high standards at the small cells.
But people claim that they did a little bit fast. They reach the point a lot faster. So it's a good progress anyway.
I mean, it's a hot material, but it has, problems like, for the large scale, modules, to reach, to be competitive with silicon, that is not competitive with silicon. And also, it has to do with this LED that is that is like, it's the biggest problem of this technology. So they are moving to LED free, but if you move to LED free, the efficiency is not dropped. So, any other question? So let's thank Ioannis again. Thank you, guys.
Thank you.